My name's Darren Holmes, and today in Get Started with MicroPython on the Raspberry Pi Pico book, we're going to be looking at Chapter 10. In Chapter 10, we're going to be wiring up an LCD module to our Pico. So I want to start you off by looking at several different types of LCD displays. So the LCD displays that I have here are broken down into two groups. The group on the left are programmed parallel. The group on the right are programmed serially. So in my last video, we looked at the serial LCD display from SparkFun. So in this video, we're looking at the LCD1602 RGB module from Waveshare. When you look at the Waveshare module, there's only one connector on here, only supports the I2C serial protocol. So because this is a fairly lengthy video, I've put together a table of contents. So you can see at 0 minutes we're going to do our introduction, which you've just seen. At 3 minutes in, we're going to talk about communication protocols. So this is parallel, serial, using a UART, I2C, and SPI protocols. 12 minutes in, we're going to start Chapter 10 in our book, where we start actually hooking up the LCD display to our Pico. At 18 minutes in, we're going to do an I2C address bus scan to see how many devices show up on our I2C bus. At 24 minutes in, we're going to start talking about the PCA 9633 RGB codes. So this is for the backlighting for our LCD display. At 33 minutes in, we're going to be talking about the AIP 31068 LCD codes. So this is the controller that actually puts text onto our LCD display. At 46 minutes in, I'm going to introduce you to RGB1602.py, which is the Waveshare LCD library that makes life so much easier, and you won't have to mess around with the RGB or LCD codes. At 53 minutes in, we're going to be looking at Chapter 10, page 118, and we're going to modify the code that's in the book to use the Waveshare library. And then about 59 minutes in, we're going to come to a conclusion. So hopefully this table of contents will help you navigate this video a little easier. I just wanted to go out onto the SparkFun website. So in here we have a discussion of parallel versus serial communication. So here we have two devices. We have basically our Raspberry Pi. Pico would be this device here on the left, and it would be communicating to this device on the right. When we talk to it in parallel, we have to send all 8 bits at the same time, along with a clock pulse. When we look at serial communication, what we can see is we have a device, such as the Raspberry Pi Pico, talking to another device serially. So those data bits have to be sent one after another, synchronized to a clock pulse. So you can see in serial communications, you need a lot less data lines. So in our book, we're going to be talking about serial communications. So we have rules for serial communications. In the signal that we're sending, we have data bits, synchronization bits, parity bits, and baud rate. So in here they talk about baud rate, and you can see the baud rate specifies how fast data is sent over a serial line. We have to frame our data. So what that means is we're going to have a start bit on the line that says we're going to start sending data. Then we send our data. So our data is either 7 or 8 bits of data. We send a parity bit. Basically, the parity bit is we add up all the data bits, and if we want even parity, and the data bits add up to an odd number, we set the parity bit at 1. And then there's usually 1 or 2 stop bits to say, this is the frame it's being sent. So the synchronization bits are the start bit and the stop bits. We have the parity bits, which I just talked about. So then they talk about wiring the hardware. So you can see on here we have a device that has a transmit and a receive. And on the receiving end, we have a transmit and a receive. So when we're transmitting data, it has to go to the receive line of the receiving device. And it's going to send back data to our transmitting device, so it goes from its transmit line to our receive line. And we need a common ground between them. So typically our signals are generated 0 to 5 volts by our microprocessor. But when we transmit on the RS-232 format, we convert our 0 to 5 volts into minus 13 to plus 13 to overcome extra noise in our circuit. So you can see they discuss UARTs, and a UART is a device that converts parallel data into serial data. So a UART is a universal asynchronous receiver transmitter. So you can see here we have our 8 data lines along with some control lines. And those are converted to our RX and TX lines. So in order to find out a little bit more about our serial communications, I found this particular website that has a graphic showing all 3 types of serial communications in one page here. So here's our UART with a Raspberry Pi talking to one device. So when we use serial communications, specifically using a UART, we could only talk to one device. If we talk over SPI, so SPI can talk to multiple devices, but we have to have a chip select line connected to each individual device. So our Raspberry Pi can talk to device 1 when chip select is talking to device 1. It talks to device 2 when chip select 2 is enabling device 2. Or it can talk to device 3 when chip select line 3 has enabled device 3. I2C, you can see, has 2 lines, a data line and a clock line, and it can be hooked up to multiple devices. It's able to hook up to multiple devices because it actually sends an address along the line. So if the address is for device 1 will talk to the Raspberry Pi. If the address is for device 2 or device 3, then they can talk to the Raspberry Pi. So there's more information on these serial protocols over at learn.sparkfun.com. So when we're talking about I2C communication, we can actually have one controller talking to 2 devices, and it separates the 2 devices by the device's address. We can also hook in a second controller, so we could actually have 2 Raspberry Pis talking to 2 different peripherals. And they would talk to each other because they would know what their internal addresses are. In here it tells us what's wrong with serial UART ports, and that is they can only talk to one device. So in here they say what's wrong with SPI. You'll notice from this diagram we can have multiple devices on the SPI bus. Unfortunately, each peripheral needs its own chip select line, and we can only have one controller. So in here they give us an example of the data that's sent over I2C. So you can see on the SDA line we have to send it the 7-bit address for the device that we're going to talk to, followed by 8 bits of data. So one last thing I wanted to talk about was the ASCII character set. So you can see I went to Wikipedia to kind of find out what it stood for. So ASCII is an abbreviation from American Standard Code for Information Interchange. So I went out on the internet and found an ASCII table. So this particular table goes up to 127, which is 7F in hexadecimal, so that's a 7-bit number. If we add 1 to 7F, it becomes 80. So all the numbers from 80 to FF are part of the 8-bit numbers. So typically we only use a 7-bit ASCII table. The important things to note is if you look at an uppercase A, it is hex 41. A lowercase a is hex 61. So sometimes when you type in a password, you get the upper and lower case mixed up, and it comes back and says incorrect password. That's because a uppercase A is 41 and a lowercase is 61, and they are not identical. You'll also note that the numbers 0 through 9 have their own code, starting at 30 and going up to 39. Even the space key has a number of 20. The numbers 0 through 31, or 0 through 1F, are usually special codes. So we start with special code null. So 0 is null. 7 is the bell. So if you printed character 7, you would actually hear a beep on your monitor. Character 8 is a backspace. So you can see we have in here line feeds, form feeds. 13, or D, is a carriage return. So when you print something and then end the line with a character 13, it gives you a carriage return. Sometimes a carriage return will also give you a line feed, but sometimes you have to put the line feed in separately. So you can see the escape character is 27. So it's highly recommended that you do find yourself an ASCII table and keep it handy so that you know what some of these codes are. So coming back to chapter 10 in our book, you can see that we're going to be talking about digital communication protocols using I2C and SPI. So you should have a little bit of an understanding of the difference between parallel and serial now. And we're not going to be using the UART. We're going to be using I2C and SPI protocols to talk to an LCD display. So in the book it says sometimes you may find that there is a MicroPython library that you can use where somebody's already converted the low-level functions into an easy-to-use interface. However, this isn't always the case. So in our case today, what we're going to do is we're going to show you how to use I2C and SPI communications to send control codes rather than using a MicroPython library. Now there is a reminder here about voltage levels. Some of these devices, I2C and SPI, can also operate at 5 volts. So please make sure that the devices that you're using are 3.3 volt compatible. 5 volts will damage your Pico. So when you look at the Raspberry Pi Pico, you'll notice that each of the pins can be set up for I2C. So that's all the pins that are in blue here. But when you take a look at the labeling, for GPIO 0, it's labeled I2C 0 SDA. And when you look at GPIO 4, it's also labeled I2C 0 SDA, which means you can only decide which of these two pins you're going to use. So the same thing with I2C1. You can see that's duplicated in several places too. So all I'm seeing here is I2C0 and I2C1, and those zeros and ones seem to be duplicated, so it looks like there's only 2 I2C channels available to you. So keeping these groupings in mind, you just have to pick which group of pins you're going to be using for your I2C communications. So in the book we're going to be using general purpose IO 0 and 1, which are on pins 1 and 2. So your SDA line will go to pin 1 of the Pico, and your SCL line will go to pin 2 of the Pico. So you can see in figure 10-2, they're showing you how to wire up the SIR LCD module for I2C to your Raspberry Pi Pico. So the Waveshare LCD display comes with a cable. All you have to do is get it in the right way around and slide it on and let it snap in. Now looking at the color of the wires, you can see they're not really color coded in any specific way. So VCC is going to be green, ground is going to be purple, blue is our clock, and yellow is our data line. So keeping in mind that the purple wire is ground, it comes with a female type connector on the end, so we can just hook it directly up to our Pico pins. So the purple needs to go to the ground pin. And remember, ground is on pin 38. Next, the green wire is the VCC, and we want to run it to 3.3 volts. So once again, looking at the bottom of our Pico, we can see 3.3 volts is on pin 36. So we can just hook that directly onto pin 36. And then we're going to hook up the clock and the data line. So the data line is yellow, and that goes to GPIO 0, which is pin 1 on your Pico. Then the blue line is the clock signal, and we have SCL going to GPIO pin 1, which is actually pin 2 on your Pico. So that's all the wiring we need to do. So as soon as you plug your Raspberry Pi Pico into the USB port, everything will get powered up at once, the Pico and the LCD display. Now you notice on this particular LCD display, the backlight has not been activated. So it looks like it's kind of a dark bluish color. You also notice on here I have like little square blocks, and they go from one end of the screen to the other, all on the first line. So these little blocks, if you can look close enough, they're made up of 5 by 8 dots. So each block is 5 dots wide by 8 dots high. So when you see something like that go across a screen, it means the screen has not been initialized. So there's a certain setup sequence we have to go through in order to initialize our LCD display. And we also need to be able to turn on the backlighting somehow. So those are two things that I notice right off as soon as I plug in this display. So it says in the book you should be able to find the address of your device in the documentation, but you can scan an I2C bus to see what addresses are currently in use. So we only have one LCD display hooked up to our I2C inputs, so I'm going to run this piece of code to find out what my I2C address is. So I've entered the program into Thonny. So you can see we're going to be importing the machine library. The data line is going to be on pin 0. The clock line is going to be on pin 1. So that's on our Raspberry Pi Pico. Then we put this line in. I2C equals machine.I2C, and the 0 means that we're going to be using I2C 0. And you can see the pin has to be sent over into the function, so SDA equals this SDA, and SCL equals this SCL. And we're going to run it at a frequency, and it looks like it's 400 kilohertz. Then finally to the screen, we're going to print I2C. So that's the object I2C, and the method is a scan. So let's go ahead and run this and see what it looks like. So you can see when I do the scan, I come up with 3 separate I2C controller addresses. When I do this using the SparkFun serial LCD, I only get one address of 114. The SparkFun LCD only returns one address because it uses the HD44780 LCD controller, But to communicate over the serial communication protocols, it uses an ATmega 328P, which provides serial I2C and SPI. So let's take a look and see what the Waveshare LCD1602 RGB module is using. So going out on the internet, I went to waveshare.net and found the datasheet for the LCD1602 RGB module. So under section 1, functions and features, you can see it's a 16 character by 2 lines. And you can see we have an LCD controller, which is the AIP 31068L, and a separate RGB controller, which is a PCA 9633DP2. So when you scroll down to the block diagram, you can see we have ground, VCC, data, and clock coming in, going to the AIP 31068L controller, and it controls the 16 by 2 line LCD display. You'll notice the lines also separate and go out to a second controller, and this is the PCA 9633DP2, and that's connected directly to the RGB backlight. Now this particular controller isn't just used on LCD screens, so it can be used to control many RGB lights. So the LCD controller has one address. The RGB controller has the other 2 addresses. So you can see scrolling through the document a little further, they gave the address for the RGB controller as C0 and the LCD controller as 7C. Now these are both hexadecimal numbers, and the one thing I want you to keep in mind is you see on this page where it says slave address, and it starts with a 0 and goes all the way across and ends with a 0. That last 0 is a read-write. So when we're using I2C, we only use 7 bits for the address, and then the 8th bit is whether the device is reading or writing from the Pico in this case. So keep that in mind when we take a look at the numbers that our scan gave us. So when you look at the scan, it returned 62, that was a decimal number, 96, and 112. So 62 in hexadecimal is 3E, and when you convert that to binary, you can see it's 11 followed by 1110, and then when you add another 0 for the read-write bit, it becomes 7C in hexadecimal. Likewise with 96, it's 60 in hexadecimal, and that is 110 followed by 4 zeros. And when you add the read-write bit, it comes out to C0 in hex. And lastly, with 112, it becomes 70 hexadecimal, which is 111 followed by 0000. And when you add that read-write bit of 0 in, it becomes E0 in hexadecimal. Okay, so now we know that 62 refers to the LCD. Those are the characters we want to display. 96 refers to the RGB backlighting. But what does 112 refer to? So I went out on the internet and found the datasheet for the PCA 9633. So if you scroll down to section 7 on function descriptions, it talks about device addresses, and please notice there's an extra S on the end indicating that there's more than one address. So if you scroll down to section 7.1.1, it talks about the addresses, and you can see here it says the PCA 9633 LED all call address. So basically the all call address is if you have multiple controllers hooked up to your I2C bus. So its address is going to be 111.0.0.0.0. Now I want you to keep in mind it says here the all call can never be used for individual device addresses. So this is used to reset or change all of your RGB controllers on one I2C bus. Also down here we have our slave address. So this is the other address that's 11000, and A1 and A0 are hardware selectable, and on our Waveshare A0 and A1 are both 0. So this is where the 1100000 comes from. So coming back to our scan list here, you can see that 62 actually ends up referring to the LCD module. That's the text we want to send to our Waveshare LCD module. The 96 refers to the RGB backlighting of this specific LCD module that we're using. And the 112, we're not going to be using it, but we need to know that it refers to all RGBs that are hooked up to our I2C bus at once. So if you're following along in the textbook, on page 118, they give you some sample code in order to say hello world on the LCD display. We haven't got quite that far yet, but I thought I would show you the code that I'm using in Thonny. So I just wanted to show you import machines the same. The SDA equals machine pin 0. Remember, this is physical pin 1 on the Pico. SCL is pin 1, which is actually physical pin 2 on the Pico. So everything is the same so far. And then they do their I2C write to address 114. We're doing an I2C write to address 96. Now this is just the code to set up the backlight display. So you can see I've put some comments in here. So we're going to go to register 1. We're going to go LED output state brightness, and it's controlled by pulse width modulation registers. So we have one for blue brightness control, green brightness control, and red brightness control. There's also a fourth LED on here. So this controller can actually do RGB A standing for amber. And then we have to set up the group duty cycle control. This is for how bright your screen is overall. And a frequency for blinking. We're not actually going to be doing blinking, so you can see I've got it set at 0. So I just want to show you where the rest of this code comes from on the data sheet. So on the PCA 9633 data sheet, you can see there's an application design information. So this is your PCA 9633. The addresses, they're just giving you an example here. This is not the addresses we're using. You can see the SDA, the SCL, and you can see there's an output enable here. We don't actually have one that's brought out on any of our pins, but it does have LED 0, 1, 2, and 3. So there is 4 LED outputs on here. This is just an example of how they're going to set up some LEDs on this particular controller. Our Waveshare LCD display, I believe, only has one LED in there. So in section 9, it talks about bus transactions. So you can see in here we have a slave address, we have a control register, and we have data for the register. So looking back at our I2C write, you can see we have our slave address, our control register, and the data to go to the control register. So these numbers in this column here are all control registers. The next column over is all data that's being sent to the control register, and this is the address for our RGBA controller. So here on the data sheet under general description, You can see it's an I2C bus controller 4-bit LED driver optimized for red, green, blue, and amber. So that's where I was picking up the amber from. So under section 7.2, they talk about the control register. So you can see the control register is made up of a few parts. We can do auto incrementing. We can do auto increment options. And there's the register address, which is what we're interested in. So you can see here, these are the auto increment options. So in section 7.3, we have our register definitions. So you can see 00 is mode 1. 02 is pulse width modulation 0. So it goes 0, 1, 2, and 3. And that's the brightness control for each of the colors of the LED. So obviously, if we have an amber in here, we're not going to be able to control it because ours is just RGB on the Waveshare. And you can see they have, here's the group, right? 06 is group duty cycle, group frequency, LED output states, and so on. Okay, so over here in Thonny, you can see I've set up all of these for you already. So what I've done is put in under control register number 2, I've found out that it's actually the blue brightness control. And if you put it at FF, it's the maximum brightness for the blue LED. So if you have the maximum brightness for the blue, the green, and the red LED, that's going to give us a white backlight. So let's run this on our Pico and see what the end result is. So you can see on our display it's fairly bright coming out of here, but your display will have slightly blue tinge to it. We haven't actually sent anything to the LCD controller, so it's still showing us an uninitialized state with all these little square boxes in it. So what I'm going to do now is I'm going to turn off the blue LED. So I'm just going to set it to 00. And I'm going to turn off the green LED. I'll set that to 00. And so all I'm going to do is have the red on at full brightness. So let's do a stop and run this and see what it looks like on our LCD display. So this is what it looks like with just the red LED backlighting on. So the next step is to actually write something to the LCD display. So this is the datasheet for the AIP 31068. It's the 40 segment driver controller for the dot matrix. This is for 2 or 3 line serial data interface. So this data sheet is a little bit hard to find, so I will put it in the description below the video. So I just wanted to bring your attention to the block diagram for the controller, and I want you to notice that we have display RAM here. So it's 80 by 8 bits. So it's not a lot of memory, but this is where we're going to be placing our data for it to show up on the display. I want you to notice that this controller has 2 types of interfaces. So there's the 3-line interface or the 2-line interface. So we have to set it up for the 2-line interface for I2C. So I'm going to start by showing you the code. It's going to be the same basic code that we started with to turn on the backlighting. So once we have that code up and working, now we can start working on the AIP 31068. And I've given you a reference page of page 20 here. So if you scroll down to page 20 of this document, you can see that there is an initialization by instruction, and it's a step-by-step guide of what you need to do to set up your LCD display. Please notice there are wait times between the instructions that you need to put in, and it gives you the entire flowchart of what you need to do to initialize your LCD display. So while the flowchart looks a little bit overbearing, this is the code for that particular flowchart. You can see we're going to start with some kind of wait sequence, and then we're going to do a function set, and I've written down notes here so that you can see what these things are actually doing. So I want you to notice a little bit about the two-line serial interface protocol that we'll be using. We have a couple of data bytes here. One is CO and the other is RS. So I want you to note that when CO is 1, so here's a control byte with a 1 in it. So when CO is 1, another control byte will follow the data byte. So we have the slave address, the control byte, the data byte, and another control byte follows the first one because CO is a 1. When CO is 0, it's the last control byte. So here we can see that CO is 0, so this is the last control byte. The other thing I want you to notice is a control byte is made up of CO, RS, and the remaining 6 bits are all 0. It also says here RS is low instruction write operation. The MPU writes instruction code into IR. When it's high, it's a data write operation, and the MPU writes data into DR. So DR is the data register, and IR is the instruction register. I also want you to note that we're using a two-line display. So the RAM that we have on our display is from address 00 to 27H. And the second line is from 40H to 67H. So in here we have an instruction table. So you can see we can clear the display. I just want you to remember that this is some data and this is RS. So wherever you see RS and it says 0, that's not just one bit. So coming back here to our two-line serial interface protocol, when we're talking about RS, it's actually a group of 8 bits, and RS is just one of those bits. And these are the data bits. Those are the other 8 that it's referencing. So RS is part of the control byte, so it's not just a single bit. The other thing I want you to note is it does take time for these things to do its little operation. So you can see if you do a clear display, you need to wait at least 1.53 milliseconds when you're using a clock frequency of 270 kilohertz. So I want you to note that all these times reference a serial interface mode where your clock frequency is 270 kilohertz. So in our code here, we should be setting a frequency of 270 kilohertz so that we have all the correct timing here. Please note in here it also says we should wait for more than 15 milliseconds. We should wait for more than 39 microseconds. So you can wait longer, you just can't wait less. So then we're going to print to the LCD display. All we need to do is say I2C write to, 62 being the address for our I2C LCD display. And 40, when we break that down, we can see C0 is equal to 0. So we're going to stream data, and RS equals 1, so it's a data write. So let's go ahead and run this code and see what it looks like on our LCD display. So looking at my LCD display, you can see it didn't display the entire message. We should have started with HE for Hello World. So I'm going to show you how you fix a problem like that. So you can see I've left a comment here. It says if full message is missing letters, increase wait time above or decrease frequency. So in here, my U times sleep, it says it was supposed to wait for more than 39 microseconds. So I've increased it to 240 microseconds. Also up here in frequency, we've got it set for 270 kilohertz. You could reduce that down to 150 kilohertz. So let's go ahead and rerun this and see what it looks like on our display. So now you can see it comes up and gives you the entire message that you wanted to print. So just to recap, what we've done is we've done our imports for machine and U time. We've set up our SDA, SCL, and our frequency. We've done the setup for the backlighting. Then we've gone through the initialization for the LCD screen. And then we've printed something to that LCD screen. So in this next piece of code, I'm going to show you how to print to any location on your LCD display. So the first part of the code, doing the setup, is identical. The second part, where we take care of the backlighting, is identical. The next chunk of code is to set up the LCD display, which is identical to what we've been doing. And here's our print to the LCD display where we said hello world. Now I'd like to print to line 2, position 5. So in order to do that, I have to tell it what part of the RAM I'm going to be writing to. So this is the setup string for it. And you can reference this against the data sheet. I have to have a sleep time in order for this particular instruction to take effect. And then I'm just going to print some text that says line 2, 5. I'm going to go to sleep for 2 seconds. Now this is a long delay in order for you to be able to read the messages that are on the display. And then I want to print to line 1. So this is the setup in order to print to the RAM address. So keep in mind, line 1 starts at 00H. Right? Line 2 starts at 40H. So then I have to do the required wait time for this instruction to take effect. And then I'm going to print line 1, position 0, but I have to put some blank spaces after it. And the reason I do that is because line 1, 0 is not as long as hello world. So if I was to write line 1, 0 on top of hello world, I would still have the RLD showing after I've done that. So I pad it with some blank spaces. So I'm going to run this and show it to you on the LCD display. So it's going to come up and say hello world, line 2, 5, and then it's going to overwrite hello world with line 1, 0. So the last piece of code I want to show you is how to scroll a message across the LCD display. And you'd want to do something like this if your message is bigger than the number of characters your display can display. So basically the code looks identical. We're going to do our same basic setup. We're going to set up the backlighting. We're going to do the same setup for the LCD display. And then we're going to do some code in here. So the first thing I'm going to do is set up a blank line. And we have a 16 character display, so that's actually 16 blanks. And then I'm going to set up a variable, and it's going to be an input. So we're going to do an input, enter your text. So it's going to sit on the screen and wait for you to enter something. You have a maximum of 40 characters you can enter, so don't enter more than 40 characters. Then the text that we're going to be printing is going to be these blank spaces plus whatever you entered in as your message plus some more blank spaces. So what's going to show up on your screen is going to be some blank spaces, each of the characters that you've entered, followed by some blank spaces as it scrolls off of the screen. So the first thing I want to do is clear my display, and then after we send it an instruction, we always have to wait for the specific amount of time that instruction takes. So then I'm going to throw in here a while true. So this is going to continuously scroll. So once you start this program, you won't be able to stop it. So it'll just keep going until you unplug your Raspberry Pi Pico. So I'm going to go ahead and run this code. And you can see down here we're going to be entering some text. So click on there and just enter whatever you want to put in there. So I'm going to say hello. Okay, so you can see this is a fairly long message. So I can't get this whole message on my LCD display, but I can scroll it across one character at a time. So when I press enter, this should send it over to my LCD display. So you can see it starts off blank and then slowly scrolls across hello class, happy to be here. And then scrolls the rest of the blanks off to clear the display so that it can start over again. Okay, so I just want to bring you back to your book that we've been using as a reference, page 116. And it says here, sometimes you may find that there's a MicroPython library you can use where someone's already converted the low-level functions in an easy-to-use interface. So I've taken you through and shown you the basics of those low-level functions. Now I'm going to show you that Waveshare has actually created a pretty nice library for us to use. So if you just go over to Google and type in Waveshare LCD 1602 RGB module, one of the first items that's going to come up is the Waveshare website. So go ahead and click on that. So this brings up all the information on the module that we were using. So what we're going to do is we're actually going to scroll down to the bottom. So I've scrolled down to resources. And here's the data sheet that I showed you earlier. So what we're going to do is click on the LCD 1602 RGB module demo. And that's going to bring up this web page. So the file we're looking for is this one here, and it's a zip file. So just go ahead and click on it. And it's going to save this to my download directory. So once it's finished downloading, I can go to my downloads directory, and you can see it's a zip file. So if you go ahead and double click on it, you can see it's got a directory in there. So I'm going to double click on it again, and it's got a directory just for the Pico. So go ahead and double click on that again. And we've got C code or Python code, so we want Python code. So in here they've got a couple of example programs, and they've got our library that we're looking for. So the library is Python code, and it's called RGB1602. So I'm just going to go ahead and grab those three files, and what I'm going to do is I'm just going to click on any one of them, and I can drag the three over and just drop it into my downloads directory, and it will unzip it for me. So now if I go ahead and double click on downloads, you can see I've extracted those three files. So what we need to do is to be able to put this onto our Raspberry Pi Pico. So I've got Thonny up and running. So I'm going to go to File. I'm going to say Open. And instead of going to the Raspberry Pi Pico, I'm going to go to this computer. And on this computer, I want to go to Downloads. And in Downloads, I want to select RGB1602.py. Once I've selected it, I'm going to click on Open. So this is the library that we need for our Waveshare LCD display. Now, typically, students just download libraries and use them. I like to go through the library and see what's in it. So the first thing in here, you can see the SDA pin is set to 4. We're going to change that to 0. And the SCL is set to 5, so we're going to change that to 1 so that it matches what's in our book. Now remember when I told you the addresses for the LCD address and the RGB address were 7C and C0? And then I said, but keep in mind they need to be 7 bits. So when you see this operator here, the greater than, and the 1, what it's doing is it's shifting all the bits over by 1. So instead of being 8 bits, it's now 7 bits. So down here we have a class called RGB1602. So when you see classes, Python is an object-oriented programming language. So in here we have to set up a class structure. I'm not going to go through this in any great detail. I just want to look through here and see what's in here. So looking through here, we can see that there's basically a function called setCursor. So we're going to be sending it a column and a row number. We have a clear in here. We have a printout. So once you've had a thorough look through this particular library and you seem to be a little bit more familiar with it, we can now save this to our Raspberry Pi Pico. So what we're going to do is we're going to go to File, and we're going to go to Save As, and we're going to say Raspberry Pi Pico, and we're going to give it the same file name that it had up here. So this is going to be RGB1602.py. And this will save the library to our Raspberry Pi Pico. So if you want to know how to use this, we can open up one of the demo files. So I'm going to go File, Open, this computer. And they've given us 2 demo files. So I'm going to choose Color and say Open. So this is going to give us an idea of what we have to do to specifically use the RGB1602 library. So we have to do an import. We have to set it up so that it knows what the size of the display is. So it's 16 by 2. Here we are. We're going to set the cursor to column 0, line 1. And it looks like it's going to print out Waveshare. And it looks like it's changing the backlighting. So we're going to go ahead and save this code onto our Raspberry Pi Pico. So I'm going to go File, Save As, Raspberry Pi Pico. And we can give it the same name. So choose underscore color. And don't forget the .py. So now we can go ahead and run this and see what the code does on our Pico with the LCD display connected. So when I press run, you can see it says Waveshare, Hello World, and then changes the backlighting through several different colors. So going back to our book on page 118, this is the example code that they're showing us. So let's take a look in Thonny and see what the minimum code is we can get away with using the Waveshare library. So bringing up Thonny, I've retyped my Hello World program in, and you can see it's a little bit different from what's in the book. All we're going to do is import the Waveshare library, which is called RGB1602. We do have to tell it that the LCD display is a 16 by 2. We're going to tell it to set the cursor at position 0, 0, so the first line, the first column, and we're going to do a printout of Hello World. So you'll notice we no longer have to set up the individual pins for SDA and SCL, and we do not have to set up the frequency because these 4 lines are taken care of inside the library called RGB1602. The setup for the LCD and the backlighting also is not required. So all we have in here is that we're going to set the cursor to 00, and we're going to print out hello world. So using a library is a lot simpler than trying to send command codes to your device, but like the book says, some devices don't have a library already written for them, so you do need to know those command codes. So let's go ahead and run this and see what it looks like on our display. So here's our output using the Waveshare library. So I know you're going to ask me for a list of all the functions that are available in the Waveshare library. So what I've done is I've gone out and I've checked them. So these are the functions that I've found. So we can set up the cursor, we can set the background color to white, we can set the RGB, so if we wanted just the red light on and turn off the green and the blue, that would be this line. We can clear the display and we can print to the display. So you're going to say, well, where did you find these? So let's take a little look at one like set cursor. So if we go into the RGB1602, and you can see there's a defined function called set cursor. We can ignore the self, but it comes in as column and row. So here's one for set RGB. So you can see we have to send it the red, the green, and the blue. Here's the clear command. Here's the printout command. And if you scroll down to the bottom, you can see a defined statement for set color white. And you can see basically what it does is it calls the set RGB function and sets each of the red, green, and blue to the maximum value of 255. So that's how I came up with the functions that were available in the RGB1602 library. So moving on to page 120 in your book, it says, of course, there's not much use in screen. It just says, hello world. So we're going to take a look at turning this into something more useful, a thermometer. So what we're going to do is we're going to take what we learned in Chapter 8 and we're going to do an A to D conversion to read the temperature sensor that's built into the Pico. So this is an internal temperature sensor. So we're going to build on this code to make standalone thermometer that doesn't need a computer to read the output. So what we're going to do is we're going to have the output of the temperature run on the screen. So you can see in here they've given us the code that we're going to try running. Now keep in mind we're going to be using the Waveshare LCD module, so we might just as well use the Waveshare's library that they gave to us. So I've gone ahead and changed the code slightly from what's in the textbook. So you can see in the textbook we have to import machine, import UTime, but in our code we have to import the Waveshare RGB1602 library. Now we don't need to declare the SDA, the SCL, or the I2C frequencies because that's already taken care of in the Waveshare library for us. But we do have to declare the displays being 16 by 2. We can then run the code as it's shown in the book until we get down here where we actually clear the SparkFun display. So we're going to do that over here with the Waveshare library. We can do an LCD clear, which will clear the display for us. We can set up the backlighting as being white, and we can set the cursor to the first column, the first row. Now we have our output string, and our output string are identical, but then when we do our write, we're no longer doing an I2C write, we're doing an LCD printout of our output string, and we do not need to put in the actual I2C address because that's taken care of in our Waveshare RGB1602 library. So let's go ahead and run this and see what it looks like on our display. So this is the output of the temperature reading on our LCD display. The next section of the book deals with Serial Peripheral Interface, or SPI. SPI is not available on the Waveshare RGB1602 module, so we're just going to skip this section. Then at the end of the chapter, we have a talking point about bit banging. So it says your Pico has 2 hardware I2C buses and 2 hardware SPI buses. So if you need more than the 4 buses that they've given you, you can actually handle this in software. And when we start using software to turn bits on and off, we refer to it as bit banging. So we're going to talk a little bit more about this when we get to our Appendix C project. So in my next video, we're going to be looking at Appendix C, Programmable I/O. And we're going to be using our Raspberry Pi Pico to connect an LED strip. And each of those individual LEDs are red, green, and blue, and we can address them individually. So please don't forget to subscribe, and don't forget to like some of my videos. Thank you for watching.